Yeah, go for it. All right, welcome everyone. My name's Hayden, and today, with the aid of Sanath, who's my academic supervisor, I'm here to present to you my personal thesis on the retrofit of electric motors to pre-existing internal combustion engine vehicles. So before we get started, I might start with something that's a little bit relatable to everyone. The craziness of fuel prices and the continuous rising of them. In the lifespan of my project, which has been less than a year, it's gone from $1.40 up to $1.60 and is now sitting at around $1.58, $1.59. With this recent and as well as future predictions for the increases of fuel costs, as well as pollution and climate change, the general public have developed a much greater awareness for their energy usage. So it is fairly well known that the internal combustion engine on light passenger vehicles have a number of deficiencies, you can say, such as it's inefficient during its start-stop periods, requires high revolutions for torque outputs, expels heat, which is not useful energy, and it has a loss of efficiency through gearing in combustion engine vehicles. So in an attempt to increase efficiency on our vehicles and lower running costs, an electric drive system is to be implemented in parallel with the combustion engine. So after conducting literature review, everyone knows that there's already hybrids on the market today. However, there is a lack for the retrofit systems for the already pre-existing millions of combustion engine vehicles. I personally believe that the general public will kind of buy into these sort of concepts, considering the take-up rates for rooftop solar and all its successes. And it's also the possibility to save the millions of combustion engines from entering landfill as electricity takes over the industry. So the design concept itself includes the use of two DC electric motors, specifically designed as hubs. That video is not playing. Specifically designed as hubs to fit on the rear wheels of the car. This is all then controlled by a Kelly controller, and it's all powered by an onboard battery bank at 72 volts. So the design is obviously to reduce load on the combustion engine by working in parallel, and is aimed at consumers that want to lower their running costs on their current ICE models. So this slide just demonstrates some of the specifications for the motor, but the motor selected is known as a brushless direct current electric motor, or BLDC that you might hear me call it. I personally wanted to use this BLDC motor in order to obviously try and save some production costs. So I didn't want to use inverters of such for AC motors. And with the onboard battery bank being a DC current source, I wanted to stay with that DC scheme of things. So some of the main benefits of a BLDC electric motor is its low upfront costs, its high instant torque characteristics, dynamic speed control, and also its low operating noise. Okay, so once all the parts were ordered and received, initial tests were then conducted in order to determine the build quality and also the wiring of the controller to make sure it's all correct. Testing was done here at the university with the aid of academic supervisors, and was done using a TD200 dyno test set. Unfortunately, as this dyno is designed for small combustion engines, we were unable to achieve accurate results for my electric motors, which obviously leads to more future testing, which leads to my next slide. Okay, so here, after installation of the motors on the car, I took it into Insane Performance just on Southside Rocky. The videos here show the capture of the data and the vehicle running. And the graphs show the torque and output obtained. So you can see that on the torque speed characteristics, it was achieved at a max torque of approximately 200 Newton meters at a speed of 5 kilometers per hour. If we then go to predict for a speed of say 0 kilometers per hour, or also known as stall, we would be expecting 250 Newton meters of torque instantly. In relation to this, the power output obtained is also approximately 8 kilowatts between the speed of 15 to 20, and this equates to nearly 10 horsepower, bearing in mind that this is for each electric hub motor. So further results obtained show the inrush of current as well as the regen braking characteristics. So the first graph of the inrush current, you can see that as the car starts to get moving and accelerating from 0 to 30, you can see that it does require a lot of current to start up, 400, but then it starts to quickly decrease as the vehicle gets going to its operating current of 100 amps. Regen is also a really great feature for this design. With the start-stop of traffic, you'll be braking a lot, so you'll be able to recharge your batteries as you're braking. So you can see, obviously, 30 to 0 kilometers per hour, we are expecting 200 amps, and as the car comes to a slow, so does the regen as well. So this is me just taking off in electric only mode. So you can see that it takes off quite nicely. These next two videos are just a little comparison of the combustion compared to electric. So you can see that in electric mode, the revs per RPM on the combustion engine doesn't actually go above its idling at 1,000. So effectively, we are saving fuel. Okay, so with that, we can then make some future cost comparisons and predictions. This first graph showing the difference between petrol and electric over distance. So obviously, I've used the same power output required through calculations, and obviously with the price of electricity, price of fuel, massive difference in how much you'll be able to save over distance. The 14,000 kilometre mark was used as the average yearly driving distance for an average Australian. This next graph then uses that 14,000 mark and predicts a yearly cost comparison. So you can see that after a 6-year period, you'll be starting to save some money. The 10,000 mark was used as the upfront cost of the electric installation. It was based off all the uses of every component that's needed for the installation, such as lithium-ion batteries and all the battery chargers and so on and so forth. Okay, so in conclusion, first of all, the measure for success was, firstly, can I get this thing installed? Like, is it feasible to install onto a car? And then secondly, does it reduce fuel consumption, and can you save money in the long run? And upon answering these two questions, I personally believe that the project has been quite successful, seeing as though I was able to save some fuel. Obviously, with this design, it's only the first iteration, so future recommendations needed to be made. Obviously, the first and biggest, most costly one will be upgrading the battery bank from a lead acid base to a lithium ion. This will also increase the cycles as well as the distance for the electric motors. Obviously, the implementation of battery chargers then is necessary. Reducing weight for better acceleration characteristics is also a future recommendation. Electric only mode, so you don't have to use combustion engine at all, as well as the possibility of renewable charging, so maybe some solar charging, charging the batteries at the same time, completely removing the cost of electricity altogether. Okay, just some special thanks to Sanath, Ian, Simon, Patrick O'Grady and Randall Stock for helping me at the uni. Thank you everyone for listening. I hope you found this presentation enjoyable as much as I did throughout the year. And if you have any questions, I'll try my best to answer them. Thank you.
We'll open it up to questions.
Tim?
So Hayden, like all good things, we plan, and sometimes things don't always go the way we expect.
Of course.
It's the deboning of something that you had planned to happen that didn't quite occur.
So yeah, one of the major setbacks for the project was obviously the installation was a little bit difficult. I kind of skimmed over that part, but I needed to fabricate a part to be able to fit the motor onto the suspension system itself. And with that came a lot of problems like roadworthiness with the tyres sticking out past the car. Obviously tried to work around those problems and do the testing where I could at the dynos, and what could be done is done, and obviously future improvements, everything in this project. Simon?
Yeah, just curious, you mentioned that it would, the 6-year mark for when that 10 grand would pay for it, start paying for itself, you start recovering costs. Just wondering if you had a chance to look into the lifetime of the parts that you would use.
Lifetime of the parts, I haven't looked into like the motors and all that sort of stuff, but the batteries obviously are a massive problem with this current model. I'm currently only using lead acid batteries at a 110 amp hour rating, and with that constant charge and discharge, they're not going to be any good in a year. So obviously upgrading it to a lithium ion base is the way to go. Other components, I haven't dived into any further details like that.
So the other question I had was just, did you get a chance to look into the performance of the hybrid vehicles such as the Toyota Prius?
Yeah, so the Prius uses a different sort of base currently. It has the electric motor in like conjunction with its combustion engine, and it does work very similar, except it can do completely electric mode and all that sort of stuff. But this design was just purely focused on the retrofit concept. So it's to save the pre-existing, like you can strap this onto your current model, as opposed to going out and buying a hybrid car at $50,000 or electric car $100,000. Ian?
You talked to a fellow that you heard about possibly registering the car.
Yeah.
Can that, I'm not sure what the version was, is it possible in future iterations to actually register the car?
Yeah, of course. So I've got a slide actually on that. So the main roads, Australia actually have a guideline to follow when fitting electric vehicles. And this is just a sort of checklist tick-off thing that you can do yourself. And then it has to be certified by a qualified engineer. At the moment, there's only that one person here in all of Rocky that's certified to do it. Unfortunately, it was a little bit too far out of scope for myself to do this and have it signed off and everything. But it is definitely in the foresight, yeah. Gil, yeah.
So I was going to ask two questions here. First up, looking at how much your batteries weigh, did you consider what sort of impacts that would have on the car's engine itself, like the extra strain and the loss of space in the boot?
Yeah, of course. So as saying, this was only the first iteration. So I wanted to save a little bit of cost on the batteries themselves. So there's the overall cost summary. The batteries used are only $65 cheapo lead acid batteries. And of course, how heavy they were would affect the handling and the suspension and everything. And the motors also affect the unsprung mass of the car as well whilst driving. But I didn't really look into that too much because I just wanted to purely focus on the fuel effectiveness. Yeah.
What did you do for the batteries?
Yeah, I didn't do anything for the ventilation. So once again, that's one of the other aspects that Main Roads looks for is the type of battery. If it's a lead acid, it needs ventilation to ventilate the hydrogen gas. But if it's a lithium ion, then you don't have to really go that route.
Hey, at the moment, do you have any control between the two?
Do I have control between the two? Yeah. So it's all done on using two separate pedals at the moment for the first iteration. And it's just done, using pedals up the front for both combustion and electric. They're completely isolated from each other because I wanted to, be able to take this apart and use my car again for the future. I didn't want to completely wreck my car, you know, but yeah, that's it's all controllable up the front, and it's going to be integrated for further iterations. Yeah, of course.
What sort of range would you get out of those?
Yes, hardly anything really. I did a little bit of testing. Like, you'd be able to drive for, seeing as though it's a 110 amp hour and it uses 100 amps, you'd be able to drive at, say, 30 Ks for an hour. So really it's only got a 30K range. But once again, saying that, it's only designed for the 30K that you're going to travel to maybe here between work, and being able to brake during traffic as well is going to also recharge those batteries for longer distances. But it's all up in the air. I haven't done those physical testings yet.
Any other questions? All right, well, thank you very much, Hayden.
Okay, thank you.
That concludes our first phase of the electrical